We have Yoshua Wuyts, and Yosh is an engineer at Prisma, a former Node hacker and currently active in Rust. He used to maintain a browser framework in JS. He has done a fair bit of work, and those were his quotes, on asynchronous both in Node and in Rust. He has 2 cats, which I have discussed with him at some point is the optimal number of cats, and he lives in Berlin. So please welcome Yosh with WASM Rust and you.
Hey everyone. Thanks for the intro.
You're welcome. I hope your cat comes on screen with you as well.
We'll have to see. I hope so too. All right. Oh, yay. Okay, I guess I'm on. Hi everyone. My name's Yash. And my talk today is. Oh, slides are not on. Okay. Sorry, I'm a little bit all over the place. Yeah, my talk today is about Rust, WebAssembly, and you. In which I hope to make WebAssembly a little bit more practical for people who are interested in it. Yay, cool. Can people see my slides? Right. Anyway, my name's Yash. I work as a Rust engineer at Prisma. What we do is we build a variety of database projects to help make database access nice and friendly in Node.js. You can try it out. It's on NPM. And we also have a website, Prisma.io. But that's not what we'll be talking about today. Today, we'll be talking about Rust and WebAssembly and how to put them together. And we'll be making things that kind of look like this. Just, the regular old 2015 demos, hello worlds, that kind of stuff. But yeah, more on that in a sec. Right. So before I dive in all the way through, I know I'm talking to, I'm guessing, majority Node.js audience, which means if I start talking, like laying down all the Rust and WebAssembly terminology on you, you might be a little bit confused. So let's get through the basics first. Right. So Rust, that's a general purpose programming language. You can build it to build very low level things like operating systems, browsers, compilers, that kind of stuff. But also very high level things like web servers, or in this case, I'll be showing you some browser fun. Right. Next up is Cargo, which is Rust Package Manager. It's kind of like NPM, but for Rust. Differences are not too big, I think. Then there's Cargo TOML, which is the package manifest format, kind of like your package JSON for NPM. Then there's WebAssembly, which is like portable bytecode. So if you're not familiar with bytecode, it's like when you have JavaScript, like the text format, you can run it through like a minifier. So you have like a smaller version, you head over to Y, send it down to like either the browser to like V8 compiling engine, like optimizing engine, which takes that representation, parses it into an AST, then like starts optimizing it and creates bytecode and like does all the fun stuff with that. So like the low level, not quite machine interpretation, but a little bit above that. So not quite assembly, but right above that. WebAssembly is much like that V8 bytecode internally. But instead of being like V8 specific, it's a portable format that's actually spec'd out and like can run in pretty much any environment. So it's kind of nice like that. And different languages can compile into WebAssembly. So Rustlang has a backend through LLVM that can compile down to WASM, which can then run in a variety of environments. WASI is another term that you might like here, which stands for the WebAssembly System Interface. In Node.js, you might be familiar with libuv, which provides cross-platform system bindings. In WebAssembly, there's a kind of like a libuv-like abstraction, which provides cross-platform system bindings specific for WebAssembly. And that's called WASI. It's got some nice properties around security, portability, upgrade stuff, which is quite nice. I might get into that a bit more if we have time. Finally, there's the WASM host, which is the environment that WebAssembly is executed in. You can kind of break it out into 3 kinds, which is a standalone environment. So imagine you have a WebAssembly program, just the bytecode, right? And you can compile that down to an x86 binary for, say, Linux. And it does all the checks, like ahead of time, it all the way down, and now you just have a regular executable that just works. The second variant is a virtualized standalone environment, right? So you take a WebAssembly program, and you have some sort of like small VM that just executes that directly on some host, which is when you're like dealing with untrusted code or, but yeah, there's no like bigger runtime environment wrapping it, which is the embedded variant. So say if you're executing WebAssembly code in the browser, or you got a game engine that says like, hey, I've got this little extension part that is a WebAssembly engine, then that's part of a larger system. That's more or less the embedded use case. And we'll be focusing the third kind, embedded, specifically towards the browser. I want to make it a little bit more practical so you can kind of see what that looks like. All right, so to get started with Rust WebAssembly today, first you need to install Rust. The way to do it is use winget or Homebrew on Windows or macOS, and you install Rust up, which is kind of like NVM, but for Rust. By default, also installs Rust and Cargo and all the other things for you. On Linux, depends on your operating system, but there's a script on the Rust website to get installed. Then second, you need a WebAssembly toolchain, because currently when you compile Rust to WebAssembly and you want to interact with like a host environment, you need to generate some Rust code, but you also need to generate some JavaScript code. And WASM tool helps you do that. So you need to install that. Cargo install is like npm install -g, so like global. Then the third step, I guess, is create a new Cargo project. It needs to be a library project for reasons. Cargo has a initializer built in, so you run Cargo new. And finally, you create a little HTML file, which includes a script tag of type module. And from there, we just add this little boilerplate, which says import init from my package. So example.js, change to the name of your example thing. And then you initialize it, pointing to the WebAssembly file. And that'll like get you going. So time for hello world. When we talk about a hello world on the web, you might think about something like this, which is a little body tag, right? Which is always there. And then inside of it, you initialize a little paragraph and you say, hello NodeConf. So in JavaScript, the way it's done is by running document create element to create a new paragraph tag. On that, or separate from that, we create a new text node to fill in the contents of that paragraph tag. Then we insert the text inside of the paragraph tag, and then we insert the paragraph tag inside of the document body. Right. Then in Rust, with a library that we're introducing today, you can do much the same. So to get started with Rust, Rust always has a main function. In this case, we have an async function main. Needs a little attribute for it for this to work. Don't worry about that. Prelude, which is a common glob import to make stuff work. Don't worry about that either. It's pretty common. And finally, we, from localhost, which is the library I've built, and you'll be seeing more of throughout this presentation. This presentation, so formal. You can import the DOM submodule, and you can get element kind, and start creating tags. So in this case, we say create a new tag of kind paragraph, and inside of it, we add a little text, hello NodeConf, and then we have a paragraph tag, which corresponds one-to-one to an actual DOM paragraph tag. And then we select the body from the DOM, and we append the paragraph tag, which, if you squint a bit, is pretty similar, right? All right, great. I sure hope so. I can't read the comment right now, so hopefully everyone's like, yes, that's very similar. Then in order to compile this, we run WASM pack build, and we give it a target web. By defaults to webpack. Yes, webpack. Sorry, I forgot the word. Yeah, we give it target web, and it compiles down, and then we have a hello world. Anyway, time for localhost. So what is that? Why does it exist? Why do we need it in Rust? Right. So this is the document, the docs.rs page for localhost. Cargo comes with a documentation tool. It's quite nice. This is the overview of the package as it stands today. You can check it out because I published it 10 minutes ago. Anyway, so the way the layering for Rust on the web works is more or less at the very bottom layer is the web platform itself. So all the APIs that the web exposes. On top of that, there's direct bindings to those capabilities. The web platform is specified using meta language called WebIDL. And in Rust, we can generate direct bindings to that. Not the nicest bindings. So on top of that, we need to create ergonomic bindings that feel natural for Rust language. So you don't need to do all sorts of weird dynamic casts. You could just use the language as you kind of would expect it would work. And finally, frameworks applications can be built on top of that. So in our current layering, there exist two projects called WebSys and JSys, which are Rust projects, Rust packages. You can get them from crates. You can add them as a dependency to your Rust project that create those low-level bindings. They're directly generated from the WebIDL definition. And on top of that, what we're introducing today is local ghost, which is very nice bindings built on top of that. And we're gradually building that out. So to give you a concrete example, if we look at a function definition, I picked the worst one from WebSys, which is a keyboard event, initializing a new keyboard event, which takes 12 arguments according to a web spec. So there's a generated version for it. This seems pretty terrible to write. So, we're wrapping it in something that resembles a bit of a nicer API, nice little methods, accessors, that kind of stuff. That just seems a bit more natural to write. Right. So that's it for like the basics and like what are we doing today. Time for some demos, more demos. Yes, great. So let's start making some HTTP requests. So the way you would like make HTTP requests in JavaScript today is using the fetch API. In order to do that, currently you still, if you want to be portable, require a self-invoking async function to have a async context in. It'll go away at some point, but for now. Then probably you want some error handling around it. So you set up a little try catch block in case anything goes wrong. We log it back out to a console instead of like throwing and like the whole thing maybe crashing down. Inside of that, we create a new request, give it a little URL, then we have a request object. Then we send that down to through fetch to actually make the request, and we get back a response. If an error occurs, we catch it. Then we have the response, which means we have the headers, but not yet the body because the body's streaming. So we await that. We say, please give me that as a string. And finally, once we have the full body read into a string, we say log the body, right, with log level info. So in Rust using localghost, we do much the same. In this case, we're importing the log and the net submodules from localghost, so we can log out to the console and we can make network requests. Here we add error handling. I'll get into that in a sec. Then we instantiate a new instance of request. We give it again a URL. Then we send that request away. That's making the fetch request. And we await for that to respond, to return. If it errors out, it goes back up. Then we get back a response. Then we read that response, the streaming body. We stream that into a string. Finally, once all of that's completed, we log it out, right? So the steps are very similar. If you run it, you get this. I just hit literally I wrote that code and I ran it and it completes like that. So there's not too much going on. Just get a UUID from HTTP bin. Yeah. So quick little sidebar, error handling in Rust. How does that work? This is a pretty common one you'll run into pretty quickly. So it's worth paying attention to just for a sec, right? So any function in Rust can return error as long as it defines a result type in its return type. So Rust, you define the signature of the functions. Here you say, hey, this thing can return an error of type IO. It's IO result. You don't need to worry about that too much. The main thing to watch out for is whenever you see a question mark in Rust, it means this is a pod where this program or this function may throw an error back up. So if you see a question mark, it just says, oh, that thing can error. Cool, right? Handle the error there. Throw it back up if there is one. And at the end, we say OK again, which goes back with IO results. And it says either, so IO result is a tuple that either returns an error kind or an OK kind. If you've written TypeScript, you might sort of be like, oh, okay, I kind of get that, right? But we always need to return OK. At some point in the future, Rust may gain try catch functionality. Try for sure, catch is a bit more up in the air. We'll see. But yeah, anyway, question mark means errors might occur here, in case you're wondering. That's the TR. Also, we bind our .await instead of prefixing it. It's a suffix. things are the way they are. I like it, but it takes some getting used to. Anyway, next up. So what we've seen so far is on the one end, we've created a DOM node in our little hello world example. Then we've moved on to make network requests. And now what if we combine the both of them? So, what if we streamed out like a bunch of server data and created DOM nodes as server data comes in? So the way to do that, probably the easiest way to do that in JavaScript is using the server-send event API. So we define a URL here. Then we say new event source, which uses the server-send event API. We initialize that. We add a little error handler there, which usually either the source is malformed or if the thing actually closes and like restarts. So we just add that for good measure. Then we move on to instantiate our DOM. So we want to create a table. And for every element that comes in, we want to append to a table. So we instantiate table element, new row. Inside that row, we create a new text node called name. So like a little column called name, a little column called data. And then finally, for every event in our event listener of type data, that's what the data stands for there, we create a new entry into the table, a new row into the table, and we append the name of the data, which in this case is data, and finally the itself, right? And then we append the whole thing onto the table. So every time like new data comes in, we add it onto a table, right? Pretty straightforward, 50 lines of code or something. Yeah. So let's do that in Rust as well. All right. I guess I'm running out of time. The way to do that is instantiate a new URL. Yes. Okay. We create an event source. We give it a URL. We define which events we're interested in. In this case, it's data. Then we create the table element. We instantiate the headings, right? It's all pretty much the same as what we've seen before. We append that to the DOM. And then finally, for every event, this is like a asynchronous for X and Y kind of loop. We create, we insert the data into the table, into a row. And this is what that looks like when we're running it. Yeah. Right. Code's pretty similar is the point I was trying to make. And it actually works. There's a demo you can find on the local. All right. You might be wondering like, okay, that's cool. We've now seen how we can instantiate Rust in the browser, how we can like use it to make network requests, create DOM elements, but how do we bind this actually to a Rust program or to a JavaScript program? And I unfortunately don't have enough time to properly go into that. There's a good guide on it on Rust WASM GitHub.io. It's pretty straightforward to expose Rust APIs to JavaScript. Just requires some manual work. But there's also a really good talk by Irina Shestak on doing this at RustConf 2019. All right. So in summary, what we've done today is so far we've created DOM nodes, HTTP requests, we've visualized, which means I've shown you like actual practical using Rust in the browser, using all the web APIs, doing a variety of things, which I think, that's not been a common theme before, I think. Anyway, future of Rust and WebAssembly.
Hi, Yash. That was a great talk. Thank you very much. I'm going to kick off with some questions, if that's okay. We've got a question from Bran, and Bran asks, what type of app or software will typically benefit from WebAssembly, and what are the obvious low-hanging fruits that we should all be looking for?
That's a great question. Thank you. So what kind of software benefits from WebAssembly? So there, like classically, the example would be like any kind of very heavy algorithmic work, anything that needs very high precision math or like very tight control about like how memory is laid out, how structures are laid out in memory. But what I'm trying to show here today is that we can start to expand beyond that. Assembly is now able to create DOM nodes to make network requests, file system operations, as far as like the browser allows it. So I think it like we'll see a trend as libraries get stabilized towards applications that have a higher level, just have like more stable requirements than Forge may provide. I think there'll be high overlap between what TypeScript, for example, tries to provide and what Rust can provide as well. So if you're building applications that are more in the line of like Photoshop, like heavy, like very intense applications, having like the structure and the rigidity, is that an English word, that Rust can provide, maybe actually prove to be very beneficial. Something I didn't quite like cover in my talk is cross-platform SDKs, for example. If you can like access the if you can make HTTP requests from Rust, you can use abstractions that like build an SDK that essentially works on Android, iOS, and the browser, but is defined in a single place. I believe Netflix recently showed something similar in Kotlin. I think that will be very interesting going forward.
Okay, thank you. So Ivan asks, what performance-wise, what is the benefit or downside of manipulating the DOM with WebAssembly?
That's a really good question. Thanks for asking. There exists a library in Rust, which is a proof of concept of a virtual DOM implementation called Dodrio. And at the time that was released, which is about a year ago, it showed performance that was on par, if not better, than other comparable virtual DOM implementations. Virtual DOM manipulates the DOM heavily, as you may know. With an upcoming proposal called interface types, actually so currently Rust calls through JavaScript into the browser. With interface types, Rust may call, unlike other languages, WebAssembly may call directly into the browser APIs. So latency will even go further down, which means we'll likely see a future in which accessing browser APIs, accessing the DOM from WebAssembly, Rust, other languages will be on par with JavaScript and possibly even faster. So yeah, hope that answers your question.
So do you think that Rust is going to replace JavaScript in the browser?
That's a pretty common question that's asked. I can't tell the future, but what I'd like to do is help bring Rust and WebAssembly to a spot where you're actually able to build full applications with it, and people actually can ask the question like, "Hey, I'm able to write a full application on the browser, in Rust. Should I do this?" Right? We're not quite there yet. At this point, we'll see like for which teams it makes sense, whether or not like Rust is accessible enough, all the other trade-offs. But I want to enable that. I at least want to make it an option. So yeah, it's a fun question. Thanks for asking.
Well, thank you ever so much. I had other questions, especially about localhost, which is an excellent name, but unfortunately we don't have time to go to those now. So thank you again, Yash. That was incredibly interesting and incredibly informative. Thank you.